All right, let's think about arc length in parametric functions. So when we've thought about arc length before, we've got some sort of curve, and we have thought about breaking it up into lots of little pieces. And those little pieces, we thought of each one as a ds, and we can break that down into horizontal and vertical components. There's a dx and a dy, and we thought about, for all of the different arc lengths we found before, we've thought about summing up those ds's along the length of the curve, all those little pieces of the curve, adding those up. And we thought about that ds was equal to the square root of dx squared plus dy squared. And in the past, we've thought about this, and we've either, out of this expression here, or we've either factored out a dx or a dy. And when we factored out a dx, we got that ds was equal to the square root of 1 plus, and then we got dy dx squared, and then we had a dx on the outside. So when we summed up these ds's, we had this, and this was our arc length formula. We could also have factored out the dy and had a dy out there, and this first thing here would become, this part here would become dx dy. But what we can do instead is we can factor out whatever the heck we want. And what would be really nice to factor out, since we've got a parametric function here, it'd be really nice to factor out, instead, factor out a dt. So we could say that ds is equal to the square root of, I'll have a dt on the outside, and so this will become dx dt quantity squared plus dy dt quantity squared. And so we could think of the arc length of a curve to be the integral of ds, which is the integral of the square root of dx dt squared plus dy dt squared dt. And we'll do it over the course of our time. And the thing is, even if a curve loops back on itself and does something like this, this idea will still work. We'll start at the starting time, t equals 0 up to whatever t equals, if it was t equals 11 or 10, since I wrote 10 there, I just do from 0 to 10, and that'll give me the arc length. Now, that's wonderful. And this is it. Now, in the problems in the book, you can do this way. And sometimes they'll ask arc length problems on the AP exam. But really, this has better applications, and application that's a little bit different. Because, well, let's think about it a little bit. Let me create a new sheet here, and but we'll come back to this one. It's right here. Okay, so here we are back on this page, and I'm taking a look at this function right here, because this is our distance traveled, our total distance traveled. Because if we look at it, we just saw that this part right here is the speed. So given some sort of position vector, this is the speed, this part right here. And if we do, and which is a rate, and this right here, dt is a time, and rate times time is distance. And so we're summing up these rate times times, which is summing up these distances, and that will give us their total distance traveled. So it's the same old thing, but probably a little different than you thought of when we were here. So this is just the speed times the time. Okay, so in class recently we've been thinking about writing a parametric function as a vector. And we can write, I don't know, if we had a vector that was, x equals position, where x equals, I don't know, t squared minus 2t, and we had a y that was equal to, I don't know, I'll say t cubed. We could write this as a vector. We could call it position vector, a vector, and we can say r, we got a little vector symbol above it, r equal to y, r is for position, I'm not sure, but r is equal to t squared minus 2t, comma, t cubed. And this is just in a vector form. So actually, on the AP, I think they often put this in parentheses rather than these braces on either side, or brackets, or whatever they're called. And this is a position vector. This will tell you the position at any given time, where the first part here is the x value, and that's the y value. It's still a vector because it does tell you location. It tells you so what magnitude and direction, or what vectors have. I don't know, but it does tell you direction from the origin. But what more important, what we can get from this very quickly is we can figure out the velocity vector. And the velocity vector is, well, you take the derivative of each of these with respect to time, and that will tell you, well, if you do that, because basically what we have here, this is equal to x, y, and if we take the derivative with respect to t, well, we'll get, well, over here we'll get, this is dx dt, comma, dy dt. And that will equal, well, it's going to be the velocity vector. And in this case, it's going to be 2t minus 2 comma 3t squared. And there's our velocity vector. And if we wanted to, we could find the acceleration vector by just taking another derivative. And the acceleration vector would be 2 comma 6t. And that would be the second derivatives of each of these, which we could write either as x double prime comma y double prime. The assumption with the prime here is that it's with respect to time, or we could write this as d squared x dt squared comma d squared y dt squared. Both would mean the same thing. Now, I want to focus on this middle set of this middle equation here, this guy here, because this is the velocity vector. And if we think about this vector, this is telling me the rate at which x is changing, the rate at which y is changing. I'm going to look at, for example, t equals negative 1. At t equals negative 1, the velocity vector would be, t equals negative 1 would be negative 4 comma 3. And what that tells me, if I think about this, it tells me that this particle is moving in the x direction to the left 4 meters per second, so I can write that as, I can think of that as negative 4, and in the y direction, positive 3. So there we go, so positive 3. So it's going to be heading in that direction, kind of up and to the left. And I could have drawn the positive 3, up 3, and then over 4. In either case, I'll start here and end there. That's the rate at which it's moving. It's moving in the kind of up and to the left. But the speed at which it's moving is the magnitude of this vector is 5. And that's the length of the vector. And the Pythagorean theorem will get it there. And you can get there by just, the square root of 4 squared plus 3 squared. But why does that mean much to us? Well, the speed is the magnitude of the velocity vector. And the speed in this case could be, well, I could find the magnitude of this vector in this specific case. But in the general case, it's the magnitude of this. This is the velocity vector. And if we think about the magnitude of the velocity vector, well, that's what we wrote on the previous page. The magnitude of this vector, because we've got a vector that is broken up into two components, there is going to be a dx dt component, which is the x speed, and there's going to be a dy dt component. And the magnitude of this is the square root of this squared plus that squared. which we've seen before. Okay, so let's look at this example problem. This is a function where x is defined as e to the t plus e to the negative 2t. Y is defined as 5 minus 2t, and we're looking at from t equals 0 to t equals 3. And this is what the function will look like. At t equals 0, x will be 2 and y will be 5. So it's right here at 2, 5. And as time increases, the y value decreases, and the x value is going to change according to this function. At t equals 3, x is going to be e to the third plus e to the negative 3, which can be relatively small. So around e to the third, which is around out here at 20 something. So there we go. So the question is, we'll have a couple questions about this. One is, what is the length of this curve? And another one I'd wonder is, what is the displacement? Well, this displacement of this particle is actually a very easy question because at t equals 0, it's here, and at t equals 3, it's here. And if I want to figure out the displacement, I don't need calculus at all. I can use the distance formula from this point to that point, and I'm done. It might not be pretty, but I'll be done at that point. Distance formula will calculate that. But if I want to figure out the total distance traveled, that's where a little calculus will come in mind. Because what happens is I have to think about distance traveled is speed versus time. Well, the speed is constantly changing. The velocity is constantly changing. And so I want to find that arc length. The total distance traveled is the length of this arc. It is... well, we got to figure it out. So let's figure out the dx dt and dy dt. Well, dx dt is going to equal e to the t minus e to the negative t, and dy dt is going to be negative 2. And so there is so my velocity vector I could think of as just that. My velocity vector would be e to the t minus e to the negative t, comma, negative 2. And the magnitude of that vector is my speed. So my speed is equal to, well, it's e to the t plus, minus e to the negative t squared, and then it's going to be plus negative 2 squared. But this is also my ds, or almost, excuse me, not my ds. That is my speed. And if I want to find the integral here, well, I'd integrate this from t equals 0 to t equals 3, and I would do, well, what is this thing? So this is e to the t minus e to the negative t squared plus 4. And then I'd multiply by dt. But what this is this is my speed times my time. So that works out pretty nicely. And it will work out pretty nicely if I do this out. Because if I do this out, I get, I get e to the 2t. And then if I multiply these two together, I get 1. So the middle term is going to be minus 1 again, so minus 2, and then plus e to the negative 2t, and then plus 4, all being square rooted dt. And then very conveniently, this simplifies a bit. This 4 cancels with this. This makes this positive 2, and now this part here is a perfect square. It is x plus e to the negative t squared. So then this will simplify to, actually, let me see if I can move this stuff up a little bit here. Ooh, look at that. I can move this up, create a little bit more space. So this becomes the, I'll move that over here. So this becomes the integral from 0 to 3 of the square root of e to the t plus e to the negative t squared dt, and which becomes e to the t plus e to the negative t dt, evaluated from 0 to 3, which then becomes the antiderivative is e to the t, and then it'll be plus negative e to the negative t, evaluated from 0 to 3. If I plug in 3, I get e cubed minus e to the negative 3. If I plug in 0, I get minus. If I plug in 0, I get 1, and then plus negative 1. So that actually cancels out. So then my total distance traveled is e to the third minus 1 over e to the third. And that would be the total distance traveled. So one question I would ask then, okay, is what is the average speed of the particle? We have this expression for the speed, and the speed was always changing. The velocity was always changing, the speed's always changing. But if you think about it, just in a very basic sense, the average speed should be the total distance divided by the total time. Well, we calculated the total distance. The total distance was e cubed minus 1 over e cubed. And that's total distance, and it took a time of 3, so total distance divided by the total time will be my average speed. And so that will be, well, it'll be this thing divided by 3. So the average speed will be 1/3 times e cubed minus 1 over e cubed as my average speed. Another way of thinking about why that has to be the average speed from t equals 0 to t equals 3 is what you could do is to figure out average anything, you integrate the speed, which is this thing right here, e to the t minus e to the negative t squared plus negative 2 squared. You integrate that from 0 to 3, and then you divide by 3 minus 0. So you integrate speed over the time period, divide by that time period, and that gets you the same answer. It's the same process as we did before, because what the top of this represents is the total distance traveled, and then divided by the time, and that will give you average speed. So hopefully that helps, and it'll help a bit on the homework tonight. So hope you enjoyed it. Thanks.